Now the question is, how do we get numerical values for the A's and D's? Well, that comes from the URDF file. The URDF's file name is KR210.urdf.zacro, and it's located in the URDF folder. URDF files are very verbose and contain many parts that we don't need to worry about right now. The most relevant section to your problem begins under the Joints heading. Here, all the movable joints are defined. For example, take a look at lines 322 to 327. This block of code identifies joint 1 as a revolute, rotating about its z-axis, and it connects the base link to link 1. The origin field defines the position and orientation of the joint relative to the parent link. But you also need information about the gripper frame that's rigidly attached to link 6. Here is the relevant code block. As you can see from lines 202 to 206, the origin of the gripper joint is 0.0375 meters in the x direction relative to link 6 and has the same orientation. The gripper joint is also a fixed joint, meaning there is no relative motion between it and its parent link, link 6. Now pay close attention to what I'm about to tell you. The thing you must recognize is that, in most cases, the joint origins in the URDF file are not consistent with the frame origins created in accordance with the DH parameter convention, nor do they have the same orientation. Unfortunately, you can't directly display joint reference frames in RViz. If you turn the robot model off, the reference frames you are able to see are actually the link reference frames. Here, I show the joint reference frame origins, indicated by black triangles, and orientations as they appear in the URDF. To keep the drawing from being horribly cluttered, I only show the origins of the DH parameter frames as a point of comparison. The other thing you need to recognize about the URDF file is that each joint is defined relative to its parent. For example, to get from joint 1 to joint 2, you have to translate 0.35 meters in the x direction and 0.42 meters in the z direction. One thing you should do as you solve this problem is verify that the transforms make sense. Each row of the DH parameter table represents the homogeneous transform between frame I-1 and frame I. In your Python code, you should incrementally check that the position of your reference frame origins are consistent with the cumulative displacements defined in the URDF file. Since the KR210 has 6 revolute joints, only the theta terms are time variables, and most of them are straightforward. The only tricky one is joint 2. Remember, the definition of theta sub I is the angle between xi-1 and xi measured about the zi axis in a right-hand sense. The manipulator was drawn in a configuration with all joint angles were assumed to be 0. But in this case, x1 is not parallel to x2 when theta 2 equals 0. There is a non-zero but constant offset of minus 90 degrees. Finally, in order to compare the total homogeneous transform between the base link and the gripper link, we need to account for the difference in orientation of the gripper link frame. The easiest way to do this is to apply a sequence of body-fixed, that is, intrinsic rotations to the gripper frame in your Python code. In order to get the two frames to align, you can first rotate about the z-axis by 180 degrees, and then about the y-axis by an angle of minus 90 degrees.